Hi, today I'm going to work through a short example, maybe it's not so short, but an example anyway, from section 3.2 to help you get used to working with the gamma distribution and the exponential distribution. Before I get started on the example, I just want to remind people that if we have a random variable that follows a Poisson distribution, with parameter lambda. Remember, lambda would be the average number of events that occur on an interval of time or area or some sort of interval. That if I am looking for the W, the time until the first event occurs, in this Poisson process, with lambda as the parameter of the Poisson, then W has an exponential distribution with parameter theta, which is the average time until the first event, equal to 1 over lambda. And if I am interested, instead of the time until the first event occurs, if I'm interested in the time, say t, is the time until the alpha event occurs. So say alpha could be 2, and maybe it would be the second event, or alpha could be 3, and it would be the time till the third event. And the Poisson process with parameter lambda for the Poisson process, then t has a gamma distribution with theta equal to 1 over lambda from the Poisson distribution, and alpha is the other parameter. It's the number of events we're looking for. So I'm going to look at how these are connected by working through an example. So here's our example. And this is the example that is available online for you to work through on your own and then come in and watch the solutions sort of with a work through so you can make sure that you're on the right track. And if you were having some trouble with this, hopefully clear up any confusion you might have had. So we're starting the situation. Suppose engineers are designing a new spacecraft. According to the manufacturer, the fuel pump that they're using is expected to fail once every 200 hours. In an individual mission, the fuel pump will be required to function for at most 50 hours. We're going to assume that failures occur according to a Poisson process, and we're going to let x be the time in hours till the first failure. So we're going to start off by answering the question, what type of distribution is an appropriate probability model for x? So here's a situation where we have a Poisson process, and we're interested in the time until the first event. So the time until the first event occurs here is going to have an exponential distribution. Now, to parameterize the exponential distribution, we need to know theta. And theta is equal to 1 over lambda from the Poisson process. And if we're thinking in terms of hours, that means we want to think about what lambda for the Poisson process would be measured in the average number of events per hour. So if it was 1 every 200 hours, it would be 1/200th of an event on average per hour. And so here our theta is equal to 1 over 200, which is equal to 200. So we've got an exponential distribution with theta equal to 200. Now, our second thing it asks us to do is to give the probability density function for x. So an exponential distribution has a probability density function that's given by f of x equals 1 over theta times e to the minus x over theta. And this is defined for values of x that range from 0 to infinity. So in this case, we can just substitute our value of theta into this exponential PDF function. So f of x is equal to 1 over theta is 200 times e to the minus x over theta, again, is 200 on the interval from 0 to infinity. So there's our probability density function for x. When we are working with an exponential distribution, the mean of an exponential distribution is equal to theta. So in this case, the expected time to the first fuel pump failure is 200 hours. And also, when we're working with an exponential distribution, the variance, sigma squared, is equal to the parameter theta squared. Just make sure this is clear. This is theta squared. So we have 200 squared. So our variance is 40,000, and that's really in units hours squared. Now we're going to start using the exponential distribution to calculate some probabilities. Question 5 asks, what is the probability that a fuel pump of this type will not remain functioning for the full 50 hours? If it doesn't keep functioning for the full 50 hours, that would mean that the time until the first event, x, is less than 50. So we're looking for the probability that x is less than 50. And we can find this by integrating from 0 to 50 our probability density function f of x, 1 over 200 e to the minus x over 200 dx. If we go through the process of doing the integration, which I'll leave you to do on your own, we get a probability of 0.2212 that the fuel pump will fail before 50 hours. And then the next question is, what is the probability that a fuel pump of this type will last longer than 50 hours? Probability that the fuel pump is more than 50 hours. Now, I could calculate this by subtracting 1 minus the probability that x is less than 50, which I already calculated. I could also find the same value by taking the integral, from 50 to infinity of 1 over 200 e to the minus x over 200 dx. Just integrate our probability density function from 50 to infinity. When I evaluate my limits, I'd have to take a limit as x goes to infinity. That also is going to end up giving me the same value. So those are ways we can work with the probability density function for the exponential distribution to answer the question. And I just want to point out that we actually could also answer this question by using a Poisson distribution. If I think about my Poisson distribution before, if I have one event every 200 hours was my lambda. If I look and make my sort of unit, equal to 50 hours. Then my lambda for 50-hour units would be, instead of 1 out of every 200 hours, I'd have 50 times 1 out of 200. So that would give me 1/4. And if I let n equal the number of events that occur in 50-hour interval of time, then n would have a Poisson distribution with lambda equal to 1/4. And so if I wanted to find the probability that x is greater than 50, well, that would mean that no events had occurred in the first 50 minutes. So that would be the same as the probability that my Poisson random variable, the number of events that occurred in 50 hours, is equal to 0, which I could find by taking my lambda, 1/4, to the x, 0, times e to the minus lambda over 0 factorial, which would give me the same answer. So often when we're working with a situation where we're looking at the time until an event occurs in a Poisson process, we could really calculate probabilities either using the exponential distribution, as we did here, or we could use a Poisson distribution to come to the same answer. Okay. Next, we're going to take a look at the second part of this example. In the second part of the example, we say to reduce the risk of catastrophe, because let's face it, having only a 78% chance approximately that your fuel pump is going to last for the duration of the flight is not probably good enough to be willing to risk it. So in order to reduce the risk of catastrophe, engineers plan to include 2 of these fuel pumps, one active and the other in reserve. If the primary pump malfunctions, the second one is automatically brought online. We're going to let y be the time in hours until the second fuel pump failure. And we want to know what the distribution is that would be appropriate to model y. So here again, we're working with a Poisson process, and we're looking at the time now not to the first event occurring, but till the second event occurring. Since we're looking for the second event, this is going to be a situation that we can model with the gamma distribution. And when we're thinking about the parameters for the model, which is question 8, our theta is still going to be 1 over our lambda from the Poisson distribution, so theta is still equal to 200. And now our alpha is saying, okay, how many events are we waiting for? Alpha is equal to 2 because we're looking at the time to the second event. To give the probability density function for y, probability density function for a gamma distribution in general is f of y equals 1 over the gamma function evaluated at alpha times theta raised to the alpha power times y to the alpha minus 1 power times e to the minus y over theta power. And if we substitute values for theta and alpha into this function, we get that in this situation, f of y is equal to 1 over gamma of 2 theta squared y to the theta minus 1. 2 minus 1 gives me 1, so times y, e to the minus y over theta is 200. And then this is for values of y that are between 0 than infinity. Just to kind of remind us, gamma of 2 in this case is 2 minus 1 factorial, so this is just 1. Theta, I should have put in a 200 here for that. So this is going to ultimately give me 1 over 40,000 times y e to the minus y over 200. So here's our probability density function. Okay. Let's see. Now we have the probability density function. We want to know what is the expected time to the second failure. So when we have anytime we have a gamma distribution, the mean of the gamma distribution is equal to alpha times theta. Kind of think about it, theta is the average time till the first event. Alpha is the number of events that we're waiting for, so it kind of makes sense. 2 times 200, which gives us 400 hours. Would be the average time until the second fuel pump fails. 11. We want to know what the variance of y is. The variance of the gamma distribution is alpha times theta squared. So we have 2 times 200 squared, which gives us 80,000 hours squared as our variance. Now we want to know what are the chances that such a fuel pump system would not remain functioning for the full 50 hours. So if the system doesn't remain functioning, it means the second failure occurs within the first 50 hours. So ultimately we're trying to find the probability that y is less than 50, which we can find working with a continuous distribution. So I'm going to say, okay, less than 50 would mean it was between 0 and 50. I'm going to integrate my probability density function, 1 over 40,000 y e to the minus y over 200 dy. To actually do this integration, you need to do integration by parts. But once you complete your integration by parts, you should get rounded to 4 decimal places, 0.0265. So by adding the second fuel pump, just to kind of remind us, before with just one fuel pump, the chance that the system was going to fail before the mission was over was 0.2212, so quite high. Reduce that quite a lot by adding a second fuel pump. Question 12 asks, what are the chances that such a fuel pump system would not remain functioning for the full 50 hours? Oh, I already did that one. But I wanted to show an alternative way of looking at this also. So we could also answer this question just as we did with the exponential. We could answer this question also, if we wanted to, with a Poisson distribution. So we'll see an alternative solution using a Poisson distribution. Let's let n equal the number of events that occur in the 50 hours. We saw before that n has a Poisson distribution with lambda for this distribution of 1/4. So now the probability that I would have y less than 50 would mean that the number of failures within 50 was at least 2. So this would be 1 minus the probability that the number of failures is less than 2, which is 1 minus the probability that n equals 0, plus the probability that n equals 1. So you can kind of think about it. It makes sense if we say, okay, if the system fails before 50 hours are up, it means that I didn't have none of the fuel pumps fail, because then the system would still be working. And I didn't have just one of the fuel pumps fail, because then the system would still be working. If either of those things happened, I would have a situation where the system's still working. But if more than 2 failures occurred, then, or 2 or more failures occurred, then the system would not be functioning anymore. So I can find the probability this way. Now I can calculate these probabilities using a Poisson distribution. And where I'm going to have my lambda, 1/4 to the n power times e to the minus lambda over n factorial plus 1/4 is 10 to the n equals 1 power times e to the minus lambda divided by my n equals 1 factorial. And once again, if I complete this calculation, I'm going to get rounded to 4 decimal places, 0.0265. So once again, just showing the connection between the Poisson and the gamma distribution and the Poisson and the exponential distribution. Thing to be careful about is to remember that depending on what units you're giving your Poisson in, here it's failing once every 200 hours. If I'm interested in time in hours, I need to convert this lambda into how many failures would occur per hour, and then take the reciprocal to get my theta. Once I'm working with situations where I'm looking at, say, 50 hours, if I want to work with the Poisson distribution, I need to figure out what the average number of failures would be for 50 hours, and that would be my lambda for that sort of Poisson process. Hope this has been helpful. If you find you have any questions, please let me know. I'm happy to answer any that you might have, either on the help discussion board or if you send me an email. So have a good day.